Next slide. This slide describes radioactivity and how we use radioactivity to get an age for these meteorites, and how we know that the solar system is 4.6 billion years ago by looking at radioactive isotopes in the rocks. Radioactivity is atoms with unstable nuclei. For some reason, they're unstable. They may either be too big, like uranium, which has the largest nucleus of the atoms, and then others have some other type of instability. For some reason, they are unstable, and they will spontaneously decay or transform themselves into another stable type of atom. When you have a large enough chunk of radioactive material, and large enough being relative to an atom, so in anything larger than a trillionth of a gram, you will see a nice regular exponential decay in this type of spontaneous transformation from an unstable nucleus to a stable nucleus. For example, uranium changing to lead. You see 1/2 of the radioactive material changing to a stable material in a certain time period called the half-life. Radioactive dating uses this exponential decay feature to measure the age of the rock. It is an absolute system in that it tells us the actual ages of the rocks in so many years. This is in contrast to what a relative age dating system would say. Well, this thing is older than this other thing, but we wouldn't be able to know how much older. With radioactive dating, we get an absolute one, so we actually know what are the number of years. This absolute system finds the ages of rocks from the fraction of the original radioactive material that is still left. The picture has the graph plot showing you the exponential sort of curve of the spontaneous transformation from an unstable material to a stable material. And then just to the right of that is a half-life clock that is ticking off the half-lives. The animation goes through 5 half-lives, but of course the rocks can be much older than 5 half-lives. In the animation, the unstable material is colored green, and the stable material is colored gray. So the green could be uranium, eventually turning into the gray lead. So how this works with the half-life is you have 1/2 of the radioactive material changing to a stable material in this half-life time period. So after 1 half-life of time, you will have 1/2 of the original amount remaining. After another half-life of time, you will have half of that. Well, half of 1/2 is 1/4, and then another half-life of time, you have half of that. So half of 1/4 is 1/8. And then after yet another half-life, you are down to having just half of that 1/8, which is 1/16, and so on. You're working with these multiples of 1/2 as you go forward and your half-life time lengths. These are the basic steps that you use in radioactive dating. The first step is the hardest one in practice, in research. It can take several months to figure this out when you're just dealing with a rock. The first step is determining the fraction of the original radioactive material that remains. In radioactive dating problems, I will give you those fractions. Then steps 2 and 3 take less than a minute to figure out. If you have a rock that started off with radioactive material and stable material both inside of that rock when it was first formed, it is possible to find out what was the original amount of the radioactive material. I described that in the Astronomy Notes textbook. It's a bit more involved process involving a higher level math than arithmetic. We're not going to worry about that here in this lecture, but I do want you to know that it is possible to do. The basic process is these 3 basic steps. Step number 1 can take a little bit more time to figure out the fraction of the original radioactive material that remains. Again, I will give you that fraction, and then you will be doing the simple steps 2 and 3. The second step is you find out how many times you would multiply 1/2 by itself to get the observed fraction remaining. That number is going to be the number of half-lives that the radioactive material has been around. For example, let's say I tell you that right now this chunk of rock has just 1/8 of the original radioactive material that it formed with. Well, 1/8 is 3 half-lives, because if you took 1/2 times 1/2 times 1/2, 1/2 multiplied by itself 3 times, you would get to the observed fraction, which is 1/8. If you had only 1/4 of the amount left, that rock would be just 2 half-lives old. 1/2 times 1/2 is 1/4. If the rock was 4 half-lives old, it would have just 1/16 of the amount left, because 1/2 times 1/2 times 1/2 times 1/2 gets you to 1/16. So again, you're working with multiples of a half to figure these out. Well, what if you have a fraction that is in between? Let's say between 1/4 and 1/8. You would know it's between 2 and 3 half-lives old. Once you have found out the number of times you multiply 1/2 by itself to get to the observed fraction, then you need to convert that to the number of years. So you would multiply the number of half-lives by the length of one half-life in years. Let's say that in this material that the half-life is 100 years. And we had in step 2, we found that it was 3 half-lives old because we had just 1/8 of the amount left. So it's 3 half-lives old, 1/2 times 1/2 times 1/2 being 1/8. So 3 half-lives old, and if each half-life is 100 years, then the rock is 3 times 100, or 300 years old. In radioactive dating problems, you'll use these basic steps, and again, I will give you the observed fraction, step number 1. Then you just do steps 2 and 3 to figure out the ages of the rocks. The radioactive dated age is when the rock solidified. If the rock is melted, the radioactive dating clock is reset. For dating once living material, such as plants or animals, we'll use the radioactive isotope carbon-14 nucleus, which has a half-life of 5,730 years. The radiocarbon dating works well for samples less than 50,000 or 60,000 years old. The Astronomy Notes textbook has a section explaining how we know that the radioactive dating method is valid, even for timescales of billions of years.